Look at me anyway. All right. So now for those of you, well, there's nobody else online. But you got to make sure you at least press this so you can hear me. And then I'm sharing my screen. Okay, so let's go to where we are today. La Lima. Now, I think I'm going to, I guess I can log in as a student. Why don't I do that? And this class is this one. All right, so where are we today? Today is August 27th, and so we're starting Chapter 3. So let me go look at the slides for Chapter 3, which would be here. And that would be in here. Here. Do I have the book here? This is a book. And I guess we can open up the, okay, so Chapter 3, you know, the book is actually better. So if we look at the book, let me put it on page display, double scroll, two scroll. And so we're going to, so now we're going to define what a key is. Along with this, we further introduce the concept of constraints, because right away with the key we're trying to enforce one particular constraint, and that's a way that we can uniquely identify a record. But we start out with a discussion on constraints. Let's see, keys. And I think we talked about constraints earlier. But okay, so let's begin with the definition of a key. Tell you what, I'm going to pull up the slides, and I'm going to have this back to refer to. So we're in Chapter 3, and while those are coming up, let's take a look at the quiz. So the quiz looks like this quiz. And so we're going to define a key, what a key is, and we're going to do it by defining these concepts of uniqueness and irreducibility. And by that, we identify what subsets of the header can be a key. So we do that, and in this, I've got two. So and then. So we introduce the concept of a key, and then we introduce the concept of a foreign key, where a foreign key is a key, but it's not a key that identifies a unique record in the table in question. It's a key that identifies a unique record in some other table. For example, okay, so then we'll define that. And we have two different database table examples. Okay. So this is a table, and I give you some possible subsets of the headers, and I ask you if any of these are a key. And if they're not a key, I want you to say which property it doesn't possess. And then I introduced the second table here. And to talk about a foreign key, you have to have at least two tables. There's the current table, and then there's the other table, the foreign table. And so here we have a table. Here, this table is students. It's not; these aren't really students, because I changed the IDs and changed the first names and so on. But it's actually from a class I taught a while ago. So these are actual majors in Scheidler, at Scheidler. And then for each, and then we have another table which has the offices and the phone numbers and the email addresses of the majors. Okay, so this table up here just has students along with their major, and then this table down here has the contact information depending on what the major is. Okay, so these two tables are related in a particular way, and they're related by a foreign key, and so you're supposed to identify the key in the foreign key here. Okay, and then the second database example here is another example, and it's an actual real example of let's say you have a database of Hawaii legislators, and it's I apologize, this is Oahu centric because there is a council on the Big Island with districts, but we're living on Oahu here. So you can imagine, there's 4 branches of government, typically. Yes, there's 4 branches of government here in, there's the federal Congress, there's the city council, there's the state house and the state senate. And so, and there's districts, there's 9 city council districts, there's, 51 state house districts, 25 senate districts, and 2 congressional districts. And so, depending on what the branch of government and the district is, this is your legislator, and these are actually real people in their offices, where the buildings are. And then again, same idea. This is the building that they have their office in, and this is the address of the building. So you're supposed to do the same kind of thing, except for in this case, I don't give you suggested keys. I just want you to tell me what the possible keys are. So anyway, that's the quiz for today. So and it's the first half of chapter 3. It's chapter 3, talking about keys and foreign keys right here. Foreign keys. And then Wednesday, we'll finish the chapter. So, so let me pull up the slides here because I want to see if they help. Oh, it's right here. So I have all the quizzes and everything in there up for the next 2 weeks. So and so they're all gonna be available the midnight of the day, and then they're gonna be available for exactly 1 week, and then you have 1 more day to hand it in after that, and then so those are all up, and they're well thought out. Should be no ambiguity. All right, so so we start out by talking about integrity constraints, which update operations will never be allowed. So, why do we talk about integrity constraints? How does this lead into integrity constraints? You may want to put a constraint on the status values of suppliers, where statuses can only range from 1 to 100. You may want to have an integrity constraint where part weight has always got to be greater than 0. That seems reasonable. So in particular, every rel var has at least is subject to at least 1 key constraint. And so it has to have one key, at least one key. It has to have at least one key. Now, you ask yourself, okay, so first of all, if you recall, the keys in our hypothetical database here, and do I not have a copy of it here? Well, anyway, you know which one I'm talking about. Let me just pop up to a copy of the database here. In this database here, where did it go? You know, we've talked about this already. The designated key in this table here is SNO. If you want to uniquely identify any supplier, you can do it just by saying what the SNO is, guaranteed. And for a part number, you can talk about any part just by talking about the PNO, and you know that also is guaranteed. That's what the definition of the key is. For this table over here, where we're talking about parts in transit by suppliers that have parts in transit, I guess. This is just that's one interpretation of this. It's good enough for our purposes here. And that requires both the SNO and the PNO to uniquely identify which tuple that we're talking about. If we're talking about, you know, this, like this one right here, let's say we're talking about this tuple here, we don't have to say, oh, the S2P1300 tuple. We don't have to say that, but we have to at least say the S2P1 tuple. We can't just say the S2 tuple because there's more than one S2 tuple. Can't just say the P1 tuple because there's more than one P1, and we can't just say the 300 tuple because there's more than one 300. Okay, so that's the idea of a key. And so one restriction that this leads us to is, well, I'll get to that in a moment. First of all, every RELVAR has to have at least one key, and it will, because we have the constraint that a RELVAR cannot have duplicate tuples. And so if a RELVAR cannot have duplicate tuples by definition, then there will be no duplicate. There will be no two tuples that have exactly every single attribute the same. And that's the definition of a key. So we can at least say if we take all the attributes together and call that the key, that works. Okay. But that doesn't follow one of the key constraints that we're going to talk about when we talk about key constraints. So, but in this case, for this hypothetical database, the supplier parts database that we're talking about, you know, this subset of the header, just this one attribute, is the key, works for the key for suppliers. Same with this one PNO for the parts, and for the supplier parts table, it's both these two. It's both the SNO and the PNO. And S name is not a key for RELVAR, and the reason is because we may want to allow more than one shipper to have the same name, which is reasonable, of course. So key. So if we define a key, it has to have both these properties. One is the one that we've talked about, which is uniqueness. And that is, no possible relation can ever be assigned, no possible relation that can ever be assigned to R has two distinct tuples that have the same K. So no two distinct suppliers can have the same key value. So, you know, no two suppliers can have the same, like S3, for example. This irreducibility means that for it to be an actual kind of key that we're talking about here, you can't reduce it. In other words, it's got to have the minimum set of of attributes in that header set that we use to define a key. So in other words, if we have a key, a defined key, that's a set of attributes, and we can actually get rid of one or more of those attributes, and it'll still be a key, then we got to get rid of those attributes for it to be a key. We have to keep on doing that until we can't do it anymore. So, for example, in this thing, we cannot have the key be SNO, comma city. I mean, it seems like that would be a reasonable key because London S1 uniquely identifies this first supplier. London S4 uniquely identifies Clark. You know, Athens S5 uniquely identifies Adam. But that doesn't work because if we combine the two and use that as the key, we are no longer able to let the database itself enforce the restriction that SNO itself has to be unique. If we define SNO itself as being unique and we try to put in another S1, the table won't accept it because that violates an easily enforceable constraint, and the database will do that. But if we define city plus SNO as being the key, then we could put in S1 Paris because S1 Paris does not conflict with S1 London. See, so it's the fact that we require irreducibility is not just because we want perfection. You know, I guess we do want perfection when we can get perfection, but it's to make sure that we can enforce all the things that we want to enforce. Now, we'll learn later that if a key or if something that is unique, in other words, if we have the first property but we don't have the second property, then that's a super key. A super key can uniquely identify a tuple or a record, but it's got more attributes in there than we need. So anyway, and that concept becomes useful later on under certain circumstances. So when we're trying to figure out if a pair, or no, if a subset of the header will work as a key, or can be a candidate primary key, then we need to make sure that both of these properties hold. So let's move on here. Now, just so when we talk about sets and subsets, there's sets, subsets, and proper subsets. And a subset that's not a proper set, can be the set itself, whereas a proper subset's got to be, have at least one less attribute than the full set of attributes. And we indicate them with this, the sideways U. You've seen that before. And the empty set is also a set, but we never consider the empty set as a key, of course. So this is the concept, or this is the this is meant to exemplify that a rel-var can have more than one key. So imagine we have tax brackets, okay, and we have this table of tax brackets, and so we have a low, if you make at least this amount, but no more than this amount. If you make at least this amount, but no more than this amount, then this is the tax that you pay, or this is the rate, the percentage tax that you pay. And so, you know, for a typical tax code, you know, I don't know how many tax brackets we have, I don't know, but there's going to be a table like this somewhere, and also you can bet that it covers that there's no holes in the table. I mean, it's not like, you know, you make a certain particular tax, or you make a certain particular income that's like in between two tax brackets, and you don't have to pay any taxes because there's no rate associated with that fee. So you'll never have that. Plus, you'll always have it where the on a particular row, the low, you know, the low is just $1 higher than the high of the lower, or the low that represents the tax bracket below it, and so on. So you also know that everything's covered. That all the possible incomes for a year, all of them are covered. So we can have anyone. We can have the and you can also assume that no two tax brackets would have the same rate. You also would assume that it's monotonic, or that it always increases, or it would always increase, I suppose, as the salaries go up, or as the incomes go up, the rate goes up. You'd think. You hope, I guess. I don't say. Unless you're a flat tax person. Okay, here. Some people think that we should just have flat tax. You know, sales tax is that. Everybody pays exactly the same tax, and that's the only way the government gets money. So then that would just be one line in this table. But anyway, assuming all those things, then any one of these three fields can be the key, because they will be unique, and you know, they would. So that would work. But you would not probably do that. For in this second case, we have it's like pilots flying a plane. They pilot, gate, day, and hour. So pilots are assigned a gate, I guess, at a particular day and at a particular hour. So you would have so. What could be the possible keys? Okay, so let's say that, well, I don't know what the possible, day and hour could be a key. Pilot, well, I'm not sure. It depends on the constraints of the thing. Let's see. What was this example? The gate, pilot and a gate. You need the day. I guess you'd always need the hour. Day and the hour. Oh, day, hour, gate, and day, hour, pilot would work. Yeah, day, hour, gate, day, hour, pilot. Because you could have a pilot and a gate going to the same, a pilot and a pilot going to the same gate on a particular day, so day, gate, pilot would not work. Day, hour would not work, because if you have more than one gate, anyway, you see that. Day, hour, gate, and day, hour, pilot. Those are the two possible key sets. So anyway. If a rel var has more than one key, then it's usual but not required to choose just one as a primary key. If a rel var just has one key, it's usual but not required to call that the primary key. Keys are fundamental, but primary keys aren't. On slides, however, when there's just one key, I'll mark it as a primary key by double underlining. Great. Okay, so now let's constraints. Every rail var is subject to at least one key constraint. It has to have, it at least has to have one key. Some rail vars are subject to foreign key constraints. Okay, so like SNO and PNO in SP are foreign keys, referring to SNO and S. SNO and SP refers to SNO and S, and PNO in SP refers to PNO and P. So we're saying that you know, this is the same as this refers to this, and this refers to this. It is you know, I learned how to. I don't know why I don't pronounce it like everyone else pronounces it, but it's more common to say the foreign key. SNO in SP is a foreign key referencing instead of referring to referencing. SNO in S. Anyway, so that's what foreign keys are. We might say foreign key constraints are glue that holds the database together. Now, you know, you're probably saying, well, how do you mean a constraint? Okay, so here's how that works. So first of all, when we define a foreign key, we talk about a K in R1 and an FK in R2. So let's think about P and O. Let's think a K in R1 and an FK in R2. So we're talking about a K in R1 and a foreign key. That's a K, a key in R1 and a foreign key in R2. So this is R2 and this is R1 and this is K and this is FK. At any given time, every FK in R2 is required to be equal to some K in R1. Okay, so that means every FK in R2 is required to be an FK. Every FK in R2 is required to have the key in S1. Okay, so every FK is required to be equal to some key in S1. In other words, this table over here has got some S1s and S2s and whatever. If there's an S1 over here, there has to be an S1 over here. Okay, that there and it's enforced. Well, you know, you can't just throw an S6 in this table. You can't just come along and put S6, you know, S6 PNO, P1, I mean, S6 SNO, P1 PNO, quantity 200. You can't just throw that in there, okay? I mean, you think, well, why not? It certainly fits the you know, key constraint. It's, you know, SNO and PNO will be unique, and there's a quantity there, and quantity is an integer, and, you know, everything else fits. Well, there's this added constraint, and that's that before you can put an S6 in here, you got to have an S6 over here. So that's a foreign key constraint. So when we set this database up, we put that in there too. We put that constraint in there too, and then now we have this perfectly good thing that's going to enforce, and the database is, you know, the database is going to do it. It also will enforce the other way, where let's say you have let's say you have S3 in there, okay? It's S3 is Blake, okay? And you know Blake's not doing too good. No, let's say Jones. No, let's say Blake. There's only one Blake. So you're over here, and for some reason you decide you want to delete Blake. It's over here. It's just this lonely suppliers table over here. You're just going to get rid of that, and all of a sudden it's not letting you get rid of it. Why is it? You know, what's going on? There's something wrong with the database. Well, no, it's because there's this thing over here. It's right here. It's this S3 needs this over here. You can't take this out. It won't let you take this out because this is still there. You have to get rid of this one first, and then you can get rid of this one. Or maybe you shouldn't be getting rid of this in the first place if this is still here. You know, that's kind of the point. Now you can also set up some other kinds of things, constraints where, okay, you know, I have this constraint, but if I'm getting rid of S3, okay, I want to get rid of S3, okay? If there's an S3 and SP, then get rid of that too. Okay, well, okay, fine, you can set it up that way. Or if you delete the S3 over here, it automatically deletes everything else but all the foreign keys that were pointing to S3. So you can do it that way too. And when you're setting up the link, when you're setting up the constraints, you choose at that time. All right, so that's the definition of a foreign key. Okay, and we call it referential integrity, the integrity of the reference. So to repeat, the foregoing definition is slightly simplified. Referential integrity can't delete a supplier tuple if to do so would leave a dangling reference, called a dangling reference, or an orphan. R1 and R2 are referenced, are the referenced and the referencing relvar. R1 is the referenced relvar. Suppliers is what's referenced, and R2 is supplier parts. That's the referring or the referencing. And K is the referenced key. K over there. So SNO in suppliers is K, and FK is SNO in supplier parts. So so that's what you need to know for quiz number, for the next quiz, or for the quiz, for quiz 3 for today. It's only 2:06, and this class goes till 2:45, right? So I'm going to cover, because there's only this many slides left, I'll cover the rest of these slides too, and then I'll figure out something else to do on Wednesday. Maybe I'll get your accounts set up and we can start fiddling around with that, and I'll finish putting up the assignment, get started with that. All right, so by the way, let's just go back quick here and see. So you should be able to figure out now from here. We have this table here, and this looks just like a table that I would get from my UH or the class. And I've just introduced some subsets of the header. By the way, 1, 2, 3, 4, 5. There's 5 attributes. How many possible headers are there? How many possible subsets are there? Can anybody tell me? Somebody. Huh? No, there's more than 9. There's more than 24. Getting closer, though. So think of it this way. So, okay, first of all, there's none of them. Okay, well that doesn't count. That would be no, 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 no. But we have no, 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 yes, no, 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 yes, no, 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 yes, yes, no, no, yes, no, 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 yes, no, yes. Is this starting to sound familiar? It's binary. It's the counting up all of the, and we've got 5 bits of a binary number, and how many binary numbers can you fit in 5 bits? 2 to the 5th power is pull your calculators out. What's 2 to the 5th power? So it's 2 to the 5 minus 1, which would be 31. So when I first started making this problem, I figured I did it in a spreadsheet, had them all down there, and I go, oh, this is crazy. So I just picked some what I think are juicy ones, and all you got to do is out of these, say which ones could be a key and which ones could not be a key. For those that could not be a key, you say why. It's either because it's not unique, or it's not or it's not unique, or it is reducible. All right, so and then for this one, okay, and then for this you just got to say what the K and what the FK and what the R2 and what the R1 are. That's pretty easy. You just got to figure it out from the examples. And then here, you just say what the possible keys are, and I describe it here. There's enough information here to say what there's just more than one possible key, and then the FK and the K. Okay, so you may notice that for the next part of the chapter, we're just talking about how we define these things. And so after the next chapter, or when this chapter is complete, then that would be the earliest possible time that I could start talking about how you actually implement this in real life. And then so I'll get our accounts set up, and then we can get into that a little bit on Wednesdays. So here we are. We're talking about chapter 3. And so after we've defined these Ks and FKs, then we just talk about how we actually define a table. What's the syntax, or what's the how do you define it? I mean, what's the syntax of the statement that you use to define it? And this is very close to an actual create table statement in SQL, where you just define the the attribute names, and you define the primitive types, and you say what the key is, and that's it. And there's a name for it, and name of the table, and these are four fields, and what the key is, and that's all there is to it. You go further. Let me switch over to this one. So this would be P&O, or parts, same thing. And if we go to SP, we say the key is this set, this pair of attributes, and we got a couple of foreign keys in there. SNO references S. In this case, the names of the attributes are the same in both tables, conveniently. Now that makes things real convenient because you don't have to specify as much. In real life, doesn't happen very often. So you have to say, SNO references S dot SNO or P dot PNO kind of thing. And so loading the database, or loading a table, or initializing a table, or your first assignment statement where you say, okay, S equals this, it would look something like this, where you have to say what all the tuples are. And so this is what that would look like. Kind of cumbersome, but it's, you just get it all, and you can use Excel and create and make it, pretty quickly. Same with, this is S insert. Okay, so this is like the assignment statement way, where you use well, this is, actually, back in the 90s when I taught the language Pascal, which is what used to be what we used to teach ICS111 and 211 back 20 years ago. This was the assignment statement. This is how it looks in SQL language. It's more like that. The trouble with this is it's clear that S is only equal to this, whereas in SQL, something like this means it's an addition. So you could be, it's like S equals S plus this, which is, whatever. And so we're just, so that's, now let's take a peek at the quiz real quick, even though we're not going to see it till tomorrow. Let me go here, and let's see. No, No, Lima. Okay, so I might as well make this available now. So I won't change the end date, but I might as well change the open date so you can take a look at it now. And I'll make it available today. But it's all you got to do is I took a subset of the L table, which is from today's quiz, the legislators table, and the B table, which is the buildings for the legislators, and these are all real. Write the RELVAR definitions for L and B as described on page 35 of the textbook. You know, like this. No. Make sure you define the headings for all the keys in each RELVAR. Use that for the key. Make sure you include the foreign key constraints. Yeah, so you got to include foreign key constraints for both L and B. So there's foreign key constraints. Write the assignment statement to assign an empty RELVAR. Okay, so first you write the definition, and then you write the assignment statement to fill it just like this. And then the third question is, you got to think about this third question a little bit. You have to think about this for about like a minute, and then you should have the answer in your head. Is there an order to which the two assignment statements can be executed in problem 2? So you're telling me you're answering the two assignment statements to assign L. Like you start with an empty L, and you can do the assignment statement, and L looks like this, and then you have this empty B, and you do this assignment statement, and B is filled, it looks like this. Is there an order in which, is there a particular order, or doesn't it matter? So that's his third question. So you can think about that. And so did I cover everything in the book? Here you're making an assignment, populating the database. By the way, most RELVARs are particularly, well, that might not be too. You're going to be both the administrator and that, so you're going to be doing both. And then at the end of the chapter, he goes through and he covers all of the different components, or when we talk about programming languages, we talk about variables and assignments and literals and values and read-only operators and comparison operators and so on. And then he talks about the parallels of a relational programming language like for databases, and then a regular programming language that you're used to. And then there's some exercises here. So what I'll do is on Wednesday, we will start with, I'll come up with what the assignment is, what the first assignment is, and it's basically, I'm going to give you this huge table, and then we're gonna create, and so we'll talk about, well, in fact, maybe I'll start with the exercises or the tables that we did for today, today and Wednesday, those tables, and I'll do some things where we'll put the constraints in there, we'll put the tables in there, we'll try to delete some records and see that it doesn't work, and mess around with changing it so if you do delete it, it deletes it in the other table and stuff, and you can kind of see how all that works in a database. So, anyway, are there any questions? All right, so I guess you guys, I don't have too much more than that. So I will see you on Wednesday. Thanks for watching.